This video is going to be more of the same in the last video, where we're going to just use phase lines to draw more solutions, but we're just going to see wackier and wackier things. We started seeing some wacky things in that last example, where yes, this is the behavior, but remember, this doesn't show how fast things are growing. And in fact, these are growing really, really fast. The book actually plots this from negative 0.00002 up to positive 0.00002. So of course, on my auto-generated plot where I didn't specify the x's, it freaked out and it was like, these slopes are too big. And of course they are, right? These are huge polynomials, so the slopes are going to be giant. So we're going to show more things that can kind of go wrong. So let's look at this differential equation, dy dt equals 1 plus y squared. Another very nice differential equation. Deceptively nice, right? But again, it's continuously differentiable, meaning that its derivative is continuous. So we have the existence of a solution, we have a unique solution, which is all wonderful. All right. Now, if you actually sketch these, and I actually don't want to go through the whole effort of doing that, you can do that right now. You could pause the video and do it a bit, but when you create your phase line, you're going to get an equilibrium point at y equals -1. And then again, it's going to be increasing below and above here, which is fine. And when you go through and find all your sketches, you're going to get something pretty interesting. Specifically, you're going to have the equilibrium solution of y equals -1. And you're going to have many, many solutions that essentially are shooting off to infinity. And they have vertical asymptotes. So remember that solutions don't have to exist for all time. The existence theorem tells us that we know we have solutions that exist, but it does not say that the solutions to a particular differential equation will exist for all time. So, and specifically what we have right here is this is the solutions to this differential equation, which again you could find if you solve this by hand. The solutions to this differential equation are -1 minus 1 over t plus a constant, depending on what the initial condition is. And so yeah, these are going to have vertical asymptotes whenever t is equal to -c. So these will have vertical asymptotes, and after those vertical asymptotes, some funny things are going to happen to this function because it's a transformed reciprocal function. So this is just like a quick warning, right? Solutions will not exist for all time. So we have to think about what the domain of our solutions might look like. But anyway, let's go on to another example. Again, it's very important to label your axes. I get sloppy a lot. I don't get sloppy. Do as I say, not as I do. Are we graphing time, the dependent and independent variable? Are we graphing the derivative? Are we graphing the derivative of the derivative? Who knows? All right. Nobody will know unless you label your axes. So another example here. Let's consider another autonomous differential equation, but this time we have a mystery autonomous differential equation. I'm not going to tell you what this function is. I will tell you that the initial condition is some initial condition. I will not tell you this either. So we have a mystery differential equation, but we know that it's autonomous. There's no t here. It's a function of only one variable. And what I want you to do is I want you to sketch a graph, or graph a sketch, kind of the same thing, of various solutions if we know this about the function f. Now, you know how I said labeling your axes is important? These are very interesting axes labels. I'm showing you that at different heights of our function, right, y is the dependent variable, at different heights of our function, I'm telling you what the derivative of that original function is. So be very careful here. And specifically, I'm saying there's some A value, some B value, and some C value. And F, which is the slope of Y, changes. Oh, let's pretend this goes through. Like so. So what I want you to do is I want you to translate this into a phase line, and then translate that phase line into a sketch of solutions for t and y. So we know the equilibrium solutions right off the bat. Why? Equilibrium solutions are the value of y that make the derivative of y 0. The derivative of y is plotted right here. F of y is y dot, or y prime, depending on how you write it. So we know the equilibrium solutions are at A, B, and C. Y equals A, y equals B, and y equals C. We know those are the equilibrium solutions. And we can plot them. Pretend these are all horizontal lines. Okay, those are the equilibrium solutions. We know this is a continuous function. Since the derivative is continuous, that means, and its derivative is also continuous, we know we have uniqueness of solutions. We know our solutions will never cross any other solutions. All right, so we can use that uniqueness theorem again, which is really, really nice. And what about the direction of these arrows? Do you think it's going down? Do you think it's going up? What do you think? Well, we just kind of have to check. Let's look at some random point. It could be this point, it could be this point, it could be this point, some point between A and B. Is y decreasing or increasing? Now be very careful. I'm asking if y is increasing, not whether this red curve is increasing. At this point, f is negative. Right? F has a negative value. This is the graph that tells you what f is. So here, f is negative. If f is negative, dy dt is negative. So between A and B, our functions are going to be decreasing. Look over here. Notice here, f is positive. So our function is going to be increasing between B and C. And over here, again, our function is going to be negative between when it's bigger than C. It's going to be positive when it's smaller than A. And again, we can use this to draw some lines or draw some curves, right? This will go off to infinity. This will be trapped between these two, trapped between these two, trapped here, and then go off to negative infinity if we're allowing for negative time. All right. So again, this is something I talked about earlier, but again, we do know that if we have uniqueness of solutions, then y, then as t goes to infinity, right? As t goes to infinity, y either goes to plus or minus infinity or in equilibrium. All right. Why is that true? Because it's got to go somewhere and it's autonomous, right? This is for autonomous ODEs. Because autonomous ODEs only depend on y. They don't depend on t. So we can never go back to where we were before, right? Why can't we go back to where we were before? Why can't we have something that looks like this green thing over time? Well, that violates uniqueness, right? Because let's look at this y value. If we're going up here, then the derivative must be positive at this y value. But over here, we have the derivative being negative at that same y value. That's not possible. The derivative is only supposed to depend on y. So this can't happen. This does not have a derivative that only depends on y. Right? If we have two pieces of the same graph and they have the same y, they have to have the same slope. All right, that's the whole idea of an autonomous differential equation. All right, so that's a little intuition for why this is true. Anyway, again, another way of saying that is each solution is going to be monotonic. It will always be increasing or always be decreasing if we have that uniqueness. Or there might be a possibility for 0, but it won't increase and decrease. Anyway, that's it for this video. We got 2 more left. The next one, we get to classify some things and introduce our second theorem of the class. Well, third if you count uniqueness and existence differently. Anyway, say hello to Hattie. We'll finish this. The math is done. You can stop the video if you don't like dogs. But she's the one that really wants to move around. She's very excited. She's being very cute right now. Anyway, bye-bye.